This is 5.9, the last lesson of the similarity unit, and in this lesson we're going to be using similarity to solve some real-world problems. So basically, we're just going to talk about two different ways that you can use similarity to solve some real-world problems, and then we'll just use kind of the same slide to do an example so that you're not spending so much time drawing the figures in your notebook. So first thing is you can use a mirror to find heights, and this is pretty cool, and we might actually take some time to go do this. But what it says is that Jim wants to find the height of a traffic light, and he can use the mirror method as seen below. So we have Jim right here. We'll label him Jim. Here he is. And he obviously wants to measure the traffic light. So what you can do, and like I said, this works in real life, is you can put a mirror on the ground. And you can line the mirror up so that when you look into the mirror, you can actually see the top of the traffic light or whatever you want to measure in the mirror. So Jim's looking down so that he can see the traffic light in the mirror. Okay. Now, the reason why this works is because we have a right angle here. So the traffic light and the ground create a right angle, and then Jim and the ground create a right angle. So we have angle and angle congruent. And then also the angle that you are looking into the mirror at and the angle that the reflection goes up to the top of the traffic light is going to be the same. So it says on the bottom there, these angles are congruent because light reflects off a mirror at the same angle it arrives. Okay, so think about like you're playing pool. It's kind of the same idea. If you hit a pool ball into the wall, it's going to come off of the wall at the exact same angle that you hit it into. Same idea here. So because of angle, we have similar triangles, okay? So to make this work, you need a few measurements, and I'm just going to kind of make these measurements up as we go here, and you can add them to the diagram. So we're going to pretend that Jim's eyeballs here, so he's looking down into the mirror. We're going to pretend that those eyeballs are 6 foot 1 inch off the ground. So Jim's a pretty tall guy, okay? And then we're going to pretend that Jim is standing like 4 feet away from the mirror. And then we're going to measure the distance from the mirror to the base of the light pole. Okay. And we're going to say that that is, let's go with 8 foot 6 inches away. Okay. Now the question is, how tall is the light pole? Okay. So what I would first do is get everything into the same unit. So right now we have feet and inches. So I would get everything the same. So remember that there are 12 inches in a foot. So 1 foot equals 12 inches. Okay, so to figure out how many inches Jim's eyeballs are off the ground, we would want to do 6 times 12 plus that additional 1 inch. Okay, so 6 times 12 is 72, plus 1 is 73 inches. Okay, so we're going to change this, or we're just going to rewrite it as 73 inches. Okay, and then 4 feet, so this distance right here, 4 feet is the same as 48 inches. I just did 4 times 12. And then 8 foot 6, so 8 foot 6, we would want to do 8 times 12 plus an additional 6, and that is going to be equal to 2 inches. All right, so that means that we're going to find the height of our traffic pole in inches. Okay, so now it's just setting up and solving a proportion like we've been doing all units. So I would maybe go with like short side to short side. So 48 inches and 102 inches. Or you're just kind of thinking about like that bottom side of each triangle. I guess you don't know for sure that it's the short side. So we can do 48 over 102 equals 73 over x. Okay, and then we're just going to cross multiply and divide. So 73 times 102, I'm going to grab a calculator, and that's going to be 7446 equals 48x. And then last step would be to divide by 48. Grab a calculator. And we get 155.125. And that's in inches. And that's fine if you leave your answer like that. What you could do if you wanted to turn it back into feet is you could divide by 12. And I'll just do that on here really quick. Just take this answer and see if I can do it like this. Divide by 12. And you're going to get close to 13 feet, 12.9 feet. And that makes sense. That seems fairly reasonable for a traffic light. Maybe a little on the short side, but not too bad. All right. Second thing that you can do to use similar triangles in real life is you can use shadows to find heights, which is kind of a cool idea. So suppose you want to find the height of a building, you can use the shadow method to estimate its height as seen below. So we have a clock tower with a shadow, and then we have a stick and a shadow. And the reason why this works is because once again, you have these right angles, okay? And then you have parallel lines right here. So this line and this line, they're parallel because the sun's rays are coming down on each of these things at the same angle. So basically, this angle here and this angle here are going to be the same because the sun is up here somewhere and it's shining down at the same angle on each of those objects. Okay. So once again, I'm just going to kind of make up some numbers here. So I'm going to say we used a yardstick. So it's 3 feet. And then the shadow was, let's just go with like 2.5 feet. Okay, so we're not going to change any units on this one. I'll keep it pretty simple. We'll just keep everything in feet. Okay, and then we don't want to go measure this clock tower. That would be too high. It'd be too difficult to measure. But we could measure the shadow. We could lay a long tape measure on the ground. And let's say that when we measured that, we got like, I don't know, 230 feet. Okay, pretty long. This clock tower might end up being really, really big, and that's okay. All right, so this is the question, is how big is our clock tower? Okay, so once again, let's put the bottoms together. So 2.5 over 230 is equal to 3 over x. Okay, so I'm going to multiply this way and multiply this way. So 2.5x equals 230 times 3. 230 times 3, 690. And then last step, divide by 2.5. And x is going to be 690. 690 divided by 2.5, which is 276 feet. That's a very big clock tower. Was it 270? 276. So maybe not super realistic on that one, but that's okay. So yeah, I think this is kind of cool and useful, and I think a lot of people who are working out in the field with math are using similar triangles and doing things like this all the time. So I thought this was a useful one to show you guys. So on the worksheet, there's 4 problems, 2 of each. Definitely let me know if you need any help with these. I didn't do a ton here, but the video ended up being 9 minutes anyway, so I'll be done, and again, just ask for help if you need it. All right, so keep working hard. If you got this far before the test, you're doing a great job. Keep working hard.